Oh, Esteban, thank you for the wonderful introduction. And I've just set up my screen here. Let's see. Start. It looks good to everyone?
Yeah.
Okay, great. Yeah, again, thank you for the introduction and good day, buenos dias to everyone in Chile and wherever you're listening from. It's my pleasure to talk about some work in my group, which we consider to be the molecular design of ionic liquids and ionic polymers for membrane separations, as well as 3D printing applications. So again, I want to just first thank everyone who's working on this. I can point to 9 people that I either in my group or collaborators and their groups who make key contributions. A lot of the work we'll see today came from Katie, who finished her PhD this spring. And she is now working at the University of Alabama in the Honors College and still working in my group. Shuai has done some work on ionic liquids, although he's also worked on many other projects. Ali as well. Gray Dennis, we'll talk some of him. Sadir and Sarav, these 2 postdocs here in the middle. They're currently working in my group on different types of polymer systems. We'll talk a lot about Ershad's work. He now left to go to KAUST in Saudi Arabia, as well as the other groups that we collaborate with, primarily Heath Turner, who's in the bottom here, who does a lot of the computations and molecular modeling, and Enrique Jackson from NASA, who's done quite a bit with me on thermal analysis of ionic liquid and polymers. So again, everyone here knows this. I don't have to go on for very long, but when we think about ionic liquids and the imidazolium type of cations, we can see that there's many different possible functional groups that we can add to ionic liquids. So back when I was working in Colorado in the group of Rich Noble and Doug Jin, I know Rich Noble gave a IMIL webinar a few weeks ago. We just were exploring a lot of different things you can do with the influence of the side chain on the properties of ionic liquids and how they would interact with gases like CO2 for separations. So we had alkyl groups, ether groups, fluorinated groups, nitriles, and ultimately also benzyl groups or phenyl aromatic groups. And so that these papers were published in 2007, 2009, and others. More recently, we just finally published some of this data just 2 years ago, even though we made the measurements more than 10 years ago. It's funny how this happens sometimes. But what we also sought to understand, and a colleague and I at the University of Alabama, we did a literature search, an extensive literature search. And, you know, again, like I showed on the previous slide, there's many possibilities for ionic liquids, right? And we know this because early on, people like Robin Rogers had said there's millions of ionic liquids, and if we mix them, we can get billions of ionic liquids, and it's absolutely true. So what we did in this paper, which was just kind of surveying the structures in the literature, we found that there's actually very few ionic liquids that are being used. And so this graphic is an illustration. It looks like mountains, maybe in Patagonia or somewhere down there, very sharp, steep mountains. Some of the ionic liquids are used quite frequently, but others are used very infrequently. So again, I won't talk much about this, but if you're interested, please read this paper because I think it sheds some light on, even though we have so many possibilities, only a few ionic liquids are actually being used. And there's maybe some good reasons for that, but also encourages that there's still many opportunities to learn quite a bit because there's quite a few things we don't know. And so one of the first things I did when I started here at the University of Alabama, this paper is now 10 years ago, was we looked at just efficient ways to go back and design imidazoles. So if we can design imidazoles, obviously we can make ionic liquids or ionic polymers. So what we have here on the top is we're just making imidazoles with various R groups. And of course, this is all known, but we can do this in high yield, and actually we don't need to use very expensive reagents. We can make a lot of imidazole very inexpensively. And so if I have imidazole with this R group, then I can make, of course, new ionic liquids, but it also allows me to make new types of monomers to make polyionic liquids, because I can add some sort of functionality that polymerizes and I get a polyionic liquid, which we'll talk about in a moment. If I do the same kind of reaction, but I have a difunctional molecule, so instead I have like dibromohexane, then I can link two imidazoles together. And this is going to allow me to do other things, right? I can design what we call ionines, which I'm going to talk quite a bit about today. Or I could do things like liquid crystals, which was a project I did in my postdoc. So again, this paper is kind of, it's 10 years old, but again, it's interesting methods that this is all very low cost, and we can make these kinds of tailored imidazoles, which can lead to tailored ionic liquids and polymers quite easily. Also, more recently, I point out too that we came up with some new approach to making vinyl imidazoles. So vinyl imidazole, obviously we cannot add vinyl chloride to imidazole like we did on the previous slide. That'd be quite difficult and dangerous. So what Ali and Katie found in a paper last year was that we can make these hydroxyethyl imidazoles at the N1 position or at the C2 position. And if we heat them in the presence of strong base at high temperature in glycerol and simultaneously apply vacuum, we can do a reactive distillation, and we can actually create new vinyl imidazoles at the 1 vinyl or even 2 vinyl imidazoles. So this is kind of really exciting because again, those can lead to new types of ionic liquids and polyionic liquids as well. Right? So they have utility as imidazoles, but also as ionic liquids. So we can see the connection here between designing imidazole to make ionic liquids. So if I'm gonna spend most of my time talking about polymerized ionic liquids and how we make these and use these. And for the most part, the literature will focus on polyionic liquids. And I know this is probably of the style of what Professor Noble talked about a few weeks ago, where we have a styrene type monomer or a vinyl monomer, and we can do some UV photopolymerization or just thermal polymerizations. And we get a structure where their cations are pendant from the backbone, and we can have the free anions. And that free anion can be something like TF2N or chloride or any number of species, just like regular ionic liquids. But then we have the ionine type of structure where the cation is in the backbone. So there's a lot of interesting things we can do with ionines, but they're a bit more challenging to synthesize. But again, these are known in the literature, and this is one of the last papers that I published before I left the University of Colorado in 2010, where we made some ionines with decyl groups, right? So we had these cations linked by decyl groups, and we made some nice membranes out of them. The membranes didn't perform all that well for CO2 separation, but they had very nice physical properties. So we start to think, what if this R group is something else? What if it's what we call high performance R group? And I'm going to talk quite a bit about that design of R groups here, because we get some very interesting materials when we choose R groups that come from more conventional polymers. So again, here's another illustration and a review paper from my group from 2019, where we compare polyelectrolytes and we compare ionines. And the ionine here, we're going to highlight different approaches that we can make some really high performance materials. There's also other reviews. I'll point out the more recent review from this year from Matthew Green's group. It had some different topics in there, as well as somewhat older reviews from Tim Long's group about 12 years ago, which kind of inspired me to get into this area, as well as a much older review from McGrath's group from almost 30 years ago now. So the idea of ionine is not new, but we haven't really studied them so much in the literature. So I'm going to draw a comparison here to the classical, or what we'd call conventional ionines on the top, versus what my group is trying to push research forward in what we call high performance ionines. So a classic ionine from early on would be some ammonium type of structure, where we can have like an ether linkage or alkyl linkage. And these are quite flexible. We see these are going to be usually hydrophilic because we have bromide type of anions. They have some limited thermal stability, because if I heat them up enough, I will get a Hofmann elimination, so that they're prone to degradation to some degree. And these were designed obviously in the days before we started thinking about modern ionic liquids. And so many of these, the halide anions, didn't think to change them to TF2N. So what we're working on in my group, and this is one example of a material that we'll talk about later on, is combining that structure, but now we're going to switch to the imidazolium cations because we can do chemistry more easily. And here we have a polyether ketone or ether ketone ether structure, but it comes from the idea of PEAK, which is a ultra high performance polymer. So can I combine the ionine idea with high performance or ultra high performance polymers? And I think you'll see the answer is yes. Even if we haven't perfected it yet, we're making great progress in this. So in my group, what really got us excited about this was the idea of making a polyimide ionine. So we had these commercially available starting materials. The first here is the aminopropylimidazole and pyromolytic dianhydride with PMDA, which is an important molecule in making polyimides like Kapton, which is DuPont product, right? It's an excellent engineering polymer. So here we were able to use the amine group on this molecule, which is commercially available, I should say. It's from BASF or others. You can buy this in pretty big scale, and simply making the imide. And so now we have these reactive reactive monomers with the imidazole N groups. And so I can take something like a dichloride molecule, this dichloroxylenes. It's just quite an easy molecule to work with. It's very reactive, and we can make a polyimide ionine. So we have the imide link, and we have the ionic groups, and we have some linkers. And we use the TF2N anion here, and it gives us nice thermal stability. And you can see here that just the neat material, we've made these excellent films, and that's probably about 12 to 15 centimeters in diameter. And we can see here the cross section. It's actually kind of boring, and there's not much going on in the material, but that's okay. It's good. It means that it's uniform, and there's no defects. But when we add ionic liquid into this structure, so we can soak this film in ionic liquid, or we can add ionic liquid when we make the film from a solvent, then we get some interesting changes in the morphology of the film. That all of a sudden we see changes, and that's reflected in the XRD, that the ionic liquid is actually ordering the polyimide. So we can see this sharp increase in the structure peaks here when the ionic liquid is present. So it actually is doing some organization of the polyimide, but it's not dissolving the polyimide. It can only absorb to a certain amount, and then that's kind of it. So here we had an interesting result that gave us some good membranes, right? So we saw too, I don't have the data on here, but that when the ionic liquid is present, they'd increase the permeability, the CO2 flux of the material about 20 times compared to the material without the ionic liquid. So the ionic liquid's making a big impact on the performance of this material. Also, just to point out too, because this will come in later, this has excellent mechanical properties. So we're thinking materials like this could be used for other applications, even like 3D printing, to make objects or structures with various geometries. So this was kind of inspiring as well, in that we have such good properties mechanically. Okay, so if we take a step back, we can really do much more than commercial available materials. We're not limited in what we can design, because here imidazole is quite a versatile starting material, and that there's many types of reactions that we can use to couple imidazoles to other functional groups or reactive functional groups. So here, and I'll remind you, everyone too, in case it's not clear, I'm chemical engineering, right? So my experience in chemistry is just by trying things and having my students, I'm not a PhD chemist. I hire some postdocs who have PhD in chemistry, but I think a lot of these reactions are quite straightforward. And so we don't have a lot of barriers to scale these materials up. So here we just take imidazole and this fluoronitrobenzene in the presence of some potassium carbonate and DMSO, and we can get this nitro imidazole kind of structure in again, pretty big yield. And then we can reduce that quite easily with palladium on carbon, ethanol, even up to 200 grams. It's really no problem to get this molecule quite pure. And that's going to allow us to do all sorts of designs, because now we can use the aromatic chemistry to make polymers. And so, of course, when you have aromatic groups, we have a lot of control over positioning. So para, meta, ortho, that all of these become possible, simply changing the reaction starting material that I just showed. Also, because aromatic groups come in all sorts of functional groups, we can have methyl groups, CF3. We can also apply this idea to methyl groups on the imidazole, so we can get these two rings to kind of rotate relative to each other out of plane. And we think that that can provide some strong impacts on the material properties, because now instead of being planar, I can rotate the rings and get some maybe different behaviors. Also, in the membrane, gas separation membrane field, thermal rearrangements types of materials are of great interest, although we haven't really quite done that yet. But having multiple types of functional groups that are reactive can give me different types of polymer architectures as well. So I highlight here the Troger's base because that's one that we're quite interested in, and I'll have some slides about that soon. So after we did the PMDA materials, Katie started making these 6-FDA materials. 6-FDA is another commercial dianhydride that's received attention in the gas separations literature because it's a non-planar bent structure. It's quite bent. So we combine the 6-FDA with different imidazole anilines. So we call them I4A, I3A, I2A, para, meta, ortho. And we can make these different monomers that are different only in the sense that the position of the imidazole is changing relative to the imide. And by the same chemistry, we can match a dichloroxylene, para, meta, ortho, to the corresponding 6-FDA compound. We can make different architectures where they are all isomers, but the positions of the groups are changed to para, meta, ortho. And when we did these, we saw that we got fairly good molecular weights. So at least about an average of 50,000, maybe a little bit higher than that. This is from Malditoff MS. So we're seeing averages at least close to 50,000, if not a little bit more. But these materials, they also had, some of them have very good thermal stabilities. So we see here at the top that the para systems without ionic liquid and with ionic liquid, so the 6-FDA, paraxylene, and you can see neat, 1 equivalent, 2 equivalents, all of these have thermal stabilities that are close to about 400 C together. The meta doesn't seem to do so well. There's some loss of material, I'm not quite sure. And then it's more severe. And then the ortho just continuously seems to be losing mass the entire time. So it might be that there's too much strain or something in the ortho material. So we chose to focus again on the paraxylene type structures and with the ethyl methyl imidazolium TF2N in the membrane itself. And also we looked at different types of ionic liquids and how those would affect the structure of the membranes. So we can see here that this benzyl ionic liquid, which I showed early on, kind of has a different effect than the EMIM or the C2MIM, right? So the type of ionic liquid that we add to the polymer is going to influence the structure, and that's going to influence overall the membrane performance. So here we can see some of these combinations, right? So here's our polymer backbone with the ionic liquid. This one is the C2MIM, or EMIM, and here we have the benzyl methyl imidazolium. And we can see then that too, the neat material, just like the prior one, these are quite boring. And even with the ionic liquid, we don't see these big effects, maybe because the 6-FDA is more flexible. So we don't see that kind of almost like exfoliation effect that we saw with the PMDA. So these membranes are quite smooth on the cross section. And you can see they're quite nice, they're transparent. These are probably about 5 centimeters diameter, something quite close to that. And then we see then for the material with no ionic liquid, the permeability is about 2, and that's a little bit low, but that's okay. But when we add the butyl, actually it's butyl ionic liquid, butyl methyl, The permeability goes to about 4.5, so it's more than doubling there. And if we go to the benzyl type ionic liquid, then we get another jump in permeability. So it says that the type of ionic liquid we add to the polymer is definitely influencing the CO2 flux. But then we see for CO2 nitrogen separation, there's actually not much change. So we can gain in CO2 flux, but we don't really lose any selectivity for CO2 nitrogen. And for CO2 methane, it's the selectivity becomes enhanced when the ionic liquid is present compared to the neat material. So that's kind of a nice result, although we do think these numbers are low, and we'd like to look at different architectures, polymer structures that can improve those CO2 fluxes. So Urshad joined my group also that year, and he had a great interest in working with this idea of what's called Troger's base, which is a 8-membered ring. You can see it here in green, this what is called Troger's base, which has been known for quite some time, but it also, again, in the membrane literature, research groups have been putting this into polymers more and more because of its non-planar. So it's thought that it will increase gas flux because it creates free volume, or what we call FFV, fractional free volume. And this is quite a versatile structure. Here you can see, even quite simply, we can do an ortho type of structure, and we can do a para type of structure. And so here we can make these ionines that have Troger's base in their backbone. So here, just an example of the synthesis. It's quite the same as what I showed earlier. We're making these aniline imidazole compounds. So here we have an ortho, here we have a para, and in the presence of formaldehyde in trifluoroacetic acid, we get quite pure materials, right? So these methods are giving us nice crystalline monomers. So it's quite straightforward, and we can see here from the NMR, these are quite pure, and it's actually quite. It's surprisingly, I was actually very happy that this was so straightforward and easy, because we already had these molecules from other work. So this was a nice way to use those again to make a different type of structure. And of course, for the ionine, then we can link these. So we chose the dichloroxylene as well as dibromodecane. So we have more rigid linker, a more flexible linker, and we made 4 different materials. And here we got, some of them were even very high molecular weight. So here we see 77 kilodaltons and 170 for the ortho. So that worked quite well. And then again, for the xylene, this one we got about 50 kilodaltons, and then the C10, we got about 96 kilodaltons. So they're quite big in terms of ionine molecular weight. So we're happy that these reactions are quite, they're efficient, and it's not all that strong of conditions. DMF 100C for 48 hours. Here we saw really nice thermal stabilities of all these materials. So here, even slightly above 400C, we don't see any real degradation. Probably what happens first when it does degrade is that it's the TF2N anion that is degrading, and then the rest of the polymer is coming. So you see a sharp decrease, which we think is the TF2N decomposing, and then the polymer backbone decomposes a bit more slowly. Also, we saw here, obviously, the influence of structure on glass transition temperature. So clearly the decyl groups, the alkane groups are more flexible. So we see lower TGs on those, and the XRD, obviously there's some influence of the structure as well. And the polymers, we should point out too, with these ionines, they're quite dense, right? Because we have these structures and we have the TF2N anion, which we know is quite dense. So these polymers have densities of about 1.3 to 1.4. We got some nice membranes here as well. You can just see here the membranes that were cast, usually from DMAC solvent, dimethylacetamide. Urshad, in this study, we didn't add any ionic liquids to the membranes. We just tested the membrane structures themselves with the charged backbone. The permeability levels are similar to what I showed earlier, but the selectivity, especially for CO2 methane, is very high. So we're quite pleased with that result, in that this is very, very high selectivity for CO2 methane separation. And I believe on the next slide, we see here that Although the permeability of CO2 is still relatively low, some of these materials we made with the Trögers-based link are as good or better than any other Trögers-based materials that have been published in the literature. That the CO2 methane selectivity here is higher than other ionic liquid polymers and higher than almost all other Trögers-based polymers. So this was quite a nice result. For CO2 nitrogen, there isn't quite as special, but this was a really good result on our mind. And how can we use this more? So this is where again we start to think about not just the membranes applications, but also more mechanical properties and how we might use those. So Ershad, he wanted to try to make some more flexible materials. So he designed this amide linkage. So here we have these dichloro kind of xylene ends, and then we have this amide link in the middle. So he linked those Trögers-based molecules with that amide group, and he saw that he had a very flexible material that had shape memory properties. And we think that's because of the hydrogen bonding that's happening, as well as the ionic charges. There's quite a bit of force holding that material together. So if we can deform it, we can actually heat it and cause it to go back to its original shape. So that was very exciting. And there'll be more about that later. Also, there's many possibilities, as we know, right? So it's not just imidazole, but we can also do things like benzimidazoles in the same respect. And here we can design Trögers-based type of molecules from benzimidazoles. So again, we've had some success doing that. And the idea there is that we create more aromatic groups around the polymer backbone, which should give us more free volume to make these materials and hopefully increase the permeability while keeping selectivity. I want to talk about this as well, this idea of a PIM, polyimide ionine, which really PIM comes from the idea of polymer of intrinsic microporosity. But to us, that refers to this central functional group with the fused ring system, which is known as the spirobisindane. And I should say this was just submitted to Macromolecules, even though it's not showing that. We just submitted this paper about 2 weeks ago. So it's the same idea, but now we have a much more rigid, bulky group because this is twisted. It's non-planar because of the spiro type of center. This was quite a bit of work in terms of the number of steps of the synthesis. We've had to go back to very small molecules, even down to orthoxylene and bromopropylene. There was many trial and error stages here and a lot of failures because we get so far along and we'd make membranes and they'd break. So I felt like we were repeating this over and over, but we finally were able to finish it. So the idea is very much the same. Ultimately, we have to make this dianhydride over here and then connect it to the imidazole, and then we make our ionine polymers using that structure. And so here we can see Ershad, he did a nice job finally making the anhydride, but it's quite a long route. Here we're seeing also the polymer that results, the NMR. Yeah, we're happy with this. The FTIR indicates everything is about what we want it to be. Again, we're getting used to seeing thermal stabilities of these materials that run to about 400 C, even a little bit more, followed by that degradation path, the quick loss of mass, which we can calculate is due to the TF2 anion, and then a more slower loss of the rest of the mass, which is probably the polymer backbone. Here, we don't see much difference in glass transition temperature. It's really quite small difference that the C10 is not much less than the xylene. So there's really not much of a difference in terms of the glass transition temperature, but it's right about 200 C. And on the side, we're just seeing some example membranes that were made for this. And again, we didn't add ionic liquids to these membranes. Ultimately, we just finished up the gas separation studies, and we saw here that the permeability of CO2, so the CO2 flux, is actually much higher than all of our previous works. In fact, quite a bit higher. And we really think that is due exclusively to the presence of that spirobasindane group. And so there's quite a big jump from polyionic liquids and our previous ionines all the way up to the PIM type of structures. And these are starting to be competitive with other membranes that have been published in the literature. So we see here we get good CO2 methane selectivity, and ultimately that does seem to be the strong point of these materials is CO2 methane selectivity. CO2 nitrogen is also pretty good compared to other materials. And then finally for CO2 hydrogen, well, it's okay. I think it's not special, but it's not bad either. So CO2 methane, of course, we can study it. It's quite easy to measure hydrogen flux because it's so fast. But really, the promising application is CO2 methane and CO2 nitrogen activity. Finally, maybe not finally, we have a lot of structures, as I mentioned, that we've tried. So here we've made benzoxazole ionines. So again, it's kind of similar to the 6-FDA previous approach, but instead we've made this monomer with the benzoxazole, which you can see right there. Also, it's quite bent, so it's non-planar. And this, again, straightforward chemistry, monomer AA, BB, we combine them stoichiometrically. And in this case, these made beautiful membranes quite easily from dimethyl acetamide solvent casting. And so that was quite nice. And here, I know it's a little bit small, but you can see here the influence of glass transition of the ionic liquid on the glass transition temperature. So without the ionic liquid present, the glass transition temperature is perhaps 180, 190 Celsius. With one equivalent of ionic liquid present, with one equivalent of ionic liquid present, you were getting some reduction in glass transition temperature to about 150. And with two equivalents of ionic liquid present, we are getting the glass transition temperature reduction to about 125. So the presence of ionic liquid, we can see too, is making these materials effectively softer. So we're becoming less glassy, reducing the glass transition temperature. So that's also quite important, I think, to membrane permeability. Here, again, more of what we call these Robeson plots. Here again, we can confirm, yeah, we're seeing CO2 methane selectivity is better than many other types of ionic liquids and other polymer materials. So we have strong hope for CO2 methane separation. CO2 nitrogen, well, it's just okay. It's kind of like everything else. And CO2 hydrogen, well, it's again, it's a difficult separation. So we don't have anything special there, but it's not anything bad either. Okay, so more recently, I think this is the last one as far as designs. We have these peak ionines, which I showed earlier. This is a little bit different approach, but we've taken some ideas here, and we've made these essentially coupled imidazole phenols to this 4,4-difluorobenzophenone. This is the classic molecule that's used for polyether-ether ketone synthesis. So we can attach those. Or we can do a coupling, an Ullmann type of coupling, although I think that my students prefer the one on the left better now because it's easier. And we can do this, make this monomer one of two ways. And again, it's a good purity as well. So we're happy with these monomers. They're quite robust and straightforward to purify. So then we can combine this again, and probably you're seeing the same thing over and over, but we have some good ways to prove we make a polymer, and then we can design further from there. So we can take that monomer, react with the dichloroxylene, and this time we have to use higher temperatures and stronger solvents like NMP at 150 C to get this material to stay soluble. Sometimes it still even precipitates during the reaction, and then we can exchange that with the TF2N. And so here we see a quite nice NMR of a very aromatic polymer. There's only one CH2, or well, two CH2 groups in the entire polymer. So we have a very aromatic backbone, which again is one of the reasons we think we can get really nice thermal stabilities from these materials is they're quite robust because we're using ionic liquids and high performance polymers. Here, what we see with the peak ionine, as we'll call it, again, lots of numbers, too many to think about here. The most important one here is though that the neat material has a permeability of about 4 barriers. And when I added the butyl methyl midazolam bistriflamide C4-MIM TF2N, that number jumps to 20. So that's about a 5 times increase in gas permeability. It's very similar to what we had very early on with the polyimide ion. And the selectivities for CO2, nitrogen, CO2, methane, they're okay. They're not as high, especially for CO2 methane compared to the other materials that we've tested. But again, we can make some nice films of these. And maybe not all of these are going to be great membranes. Obviously, peak polyether ether ketone, the regular material is not used as a membrane, but we can get good structural properties out of it, good mechanical properties. So perhaps there's other uses. So here I just want to briefly show some ideas we've been talking about recently. You saw some of this, maybe some similar ideas here on the left. We're also thinking about how we can make ionines from materials that have reactivity at both positions. So normally we're doing everything at the nitrogen N1 position, but of course, because imidazole is so versatile, we can buy other imidazoles, right? So here we can take 2-phenylimidazole and nitrate it to make the nitro, and we can couple that to another aromatic nitro. And now we can make a monomer with 2 amine groups on 1 imidazole. So that allows us to do different types of polymers. The other interesting thing too is to make these imidazole type of structures that are from benzimidazoles that are effectively bent as well, right? So we see here that we have what's called like a bi-imidazole structure, that the 2 imidazoles are linked between the 2 positions by an aromatic ring. And so there's lots of new design possibilities and how we can use these. And what we've already seen with polymers that we've made from this, I don't have all the data, is that the thermal stability goes up even more, that we're seeing thermal stabilities close to 500 C now when we take this approach and making everything even more aromatic. The other thing we've explored lately, both experimentally and computationally with Heath Turner's group, is the idea of what we call multivalent ionic liquids. And so some might say, well, you can't do this because they're going to be solids, and that's usually true, right? So in the classic definition of ionic liquids, these probably have very high melting points, and maybe they degrade. But if I want to add them to polymers, that's different. I'm not so worried about it being a liquid, that if it's going to sit inside of a polymer that's also a solid, that perhaps I get some interesting effects in terms of the free volume and the spacing, because the polymer is wrapping around some bulky type of group. And Heath Turner's group has shown that these are quite interesting. Computationally, we've done some experimental studies as well, and even making some kind of cross-linking systems out of this as well. And we think also you can do the same thing with anions, right? So I think this is an interesting structure, and we've published a little bit on this as well, that the benzene trisulfonic acid, and we can convert that to other molecules as well. So I think, again, think outside of the one-to-one pairs, especially when it comes to the materials design of ionic liquids. We don't have to follow the rules, because it doesn't have to be necessarily a liquid to be interesting in a polymer system. So I'll just also talk a little bit about some of our processing and 3D printing here with the next, I don't know, 7-8 minutes. So leave some time for questions. So early on, because we had such nice results with those polyimide ionines, I thought, can we make these as fibers or filaments, right? So can we make something more than just a membrane? And even can we do 3D printing? So as I mentioned, we scaled this up. So we made 250 grams of this, and we used this extruder, which we purchased from a company in the Netherlands called 3D Evo. So here, this is the feed top of the extruder. This is our that PMDA, I should say, polyimide ionine, and this is quite big. I think this cylinder can hold like 2 kilograms of material. So it's not even very full, but for us, 250 grams is a good amount. And here you can see we're actually extruding some filaments here. And the challenge with making filaments for 3D printing is keeping the diameter constant. So we had some difficulty there, but we can see that we're still able to extrude this material, and it becomes this kind of amber brown after being extruded. And then I said, well, if I can extrude it, can I pull a fiber? So what we did, and this is my hand here, we actually started just pulling those filaments into fiber. So if we applied force to them, we could draw them very thin. You can see here, this is wrapped around my finger like many times, right? So these, you can make quite thin fibers. And I don't think this has ever been done with ionic liquid type polymers before, making a material that can be extruded and drawn into fibers. So this is really excellent. We can see then the material turns into this almost gold color as we pull it, where it was more brown when it was thicker. But as we pulled it, perhaps we're aligning it and we're getting this golden structure. And later on, we borrowed this winding tool from another group, and we were able to kind of automate the process, so we weren't standing there all day pulling fibers. So we were able to spin them or pull them and wind them. And you can see here, I don't know, this is many hundreds of feet or meters of fiber at this point. It almost looks like hair. So this is, again, high surface area materials. Maybe it can be used for absorption types of experiments, that there's some unique surface properties. That's not something we've done, but again, it's quite promising. I think that this is even feasible. We would not think of ionic liquid based polymers as able to do this. Later on, my student Grayson, who I showed at the beginning, he spent some time making almost like yarns. So he spent some time doing this and showing that this can be done in like bundles. And so there we see this nice wound structure, and you can see it even expands. And so this is many, many hundreds of feet, I'm sure, of fiber that we've wound. And again, it's kind of proof of concept. Who knows what else we might do with that. And we see here too, these fibers. Some of them are less than 50 microns, I think, because again, the way we did it. Some of them are quite big, but you can see here too that we have, we're able to pull these. And I'm sure if we did it again in a more sophisticated manner, we can pull them even smaller. So again, that may open up new opportunities for all sorts of applications, including adsorption onto these. But I'll finish up with polyamide ionines. That's the one maybe material I didn't cover yet. And these become very interesting. And at first we were just doing this to see what would happen. Like, what is the difference between a polyimide and a polyamide? So we went back to that aminopropylimidazole with these two diacid chlorides, terephthalate chloride, isophthalate chloride. Of course, we know this TC is the main component of Kevlar. IC is the component of Nomex. These are famous engineering polymers, of course. So then we were able to make what we call the TC API with the para connectivity, and the IC API with the meta connectivity. And of course, we can polymerize these. But I do want to show also a study we did with the Haritz Sardon's group in San Sebastian, Spain at Polymat. So I was on sabbatical at Polymat in San Sebastian in 2018. I made a lot of good connections and friends there. And one of the ideas that came from this was, can we make our monomers from waste plastic? So Haritz group has an excellent ionic liquid catalyst to use decomposed PET or polycarbonates. So we're able to take our imidazole and add it to this mixture with the catalyst, and we were able to make our monomers from plastic waste. So that's quite interesting that we can, we don't have to go through the traditional route of terephthalate chloride to make these. We can actually use plastic waste to do it. So there's some hope for sustainability in these types of polymers as well. Okay, so then if I have the monomer, of course, I have my same strategies with my dichloroxylene examples, and I can make my what we call TC API paraxylene. So this one we really like. You'll see in a moment, it's got quite nice properties. So initially what we saw then was that, unlike the polyimide, which was strong but brittle, this was a bit much more rubbery. So it had some excellent resistance to impact. It had elasticity, but it was still quite strong. So here, this was Katie making this as a coil and showing the stretchability of it, and that it will come back like a spring. So again, this is quite an interesting material in what it does. And in terms of shape memory and self-healing, in fact, the self-healing, I can poke it, I can cut it, and it heals its whole very, very quickly. So when I was in San Sebastian, also with Haritz's group, we were able to do some 3D printing of these. And so here we see then on the left is the University of Alabama, and on the right is the Universidad de País Vasco, the logos of the universities, respectively. So that was our proof of concept there. And then what we did to test mechanical properties was we 3D printed the dog bone type of tensile bar structures. And what's interesting is if you're familiar with this type of 3D printing, we know that filament-based 3D printing often leaves defects, right? Or you don't get good bonding. But here, because we have a self-healing material, the boundaries or the defects are starting to close themselves. So we don't have these issues of bonding. It's almost like a continuous material, even though it's being deposited layer by layer and row by row. So you're able to make these tensile bars, and we're able to stretch them. We see here quite a steep increase here in the Young's modulus, and then a much more gradual increase. Probably we can't, it's the limit of the machine, in fact. So again, really excellent possibilities for 3D printing. And when we use those self-healing properties, this was quite fascinating. We were able to print 2D parts, 2D structures, and then we were able to assemble them in 3 dimensions. And the joints, so we purposely printed these little edges, so it's almost like they're locking together. The joints will start to heal, right? So the self-healing properties are happening spontaneously, and the edges are fusing together. So this was quite exciting that we could take a 2D geometry and assemble it in 3D, and the final part is almost as if it was made in 3 dimensions. So that's an interesting implication. And obviously we still need to perfect the material properties. There's maybe some warping, but nonetheless, you can see that those edges, those seams are disappearing. We also showed here too, this was on a different 3D printer at the University of Alabama, just printing it in different directions. Obviously, you will get different mechanical properties depending on the way that you print. And so it's better to print parallel than it is to print perpendicular to the direction of stress. Even very recently, just last week, one of my collaborators, PhD students, he was able to electrospin that same material. And it's quite interesting to me, at least because what we saw was we don't really get individual fibers. We get just one kind of continuous network of fibers, and some of them are bigger, and then we get these small links between them. So we're still thinking like what to do with this or how to use it, but it's interesting proof of concept that this material can also be electrospun, and that we see almost everything fusing together as one mesh versus individual fibers. And again, we probably have to attribute that to the self-healing properties and the spontaneous kind of welding to itself. And it's quite an interesting result. So with that, obviously there's a lot of things we're doing with membranes, and that's keep going. I think we're about to create another new generation of membranes based on what we've learned with even different structures. Of course, adding the ionic liquid to those structures is an important factor to increase gas permeability, and often it improves selectivity. We do really like the spiral Bissindane and Tröger's base concept, so I think you'll be seeing much more of that from my group in the coming years as far as our membranes go, as well as changes, new approaches to polymer backbone shapes, and these ideas of multivalent ionic liquids. And of course, lots of collaboration with Heath Turner's group on computational studies that help us even design these things better. So I want to acknowledge our funding, which comes primarily from the Department of Energy, United States, several different programs, as well as the National Science Foundation, and NASA has been supporting this quite a bit because they're very interested in 3D printing for space applications. So again, thank you very much for having me. It is my pleasure to do this webinar. today, and I look forward to answering your questions.
Okay. Thank you very much, Professor Jason, for this very wonderful presentation. Now we have a little room for questions. So you can open your microphone as always and ask directly Professor Bara, or you can write your question in the chat and I can read it for you. So questions. Well, in the meantime, I have one question. Well, I had many questions, but okay, some of them were answered during your presentation. And well, have you tested your materials in for as membranes to separate molecules from aqueous streams, or you see the possibility in the future to test your membranes to separate molecules from aqueous streams?
Yeah, I think so, Esteban. Maybe ones that I didn't show would be even more promising. We were able to make a different kind of polyamide, incredibly thin. So maybe it's good for reverse osmosis. Maybe it's good for any applications you're thinking of for aqueous streams. I think, yeah, it's a different kind of approach, and it's just not something we're set up to do, but I think it's an opportunity for sure. I'm not aware of many studies on aqueous separations and ionine type materials. So anything we would do would be the first example, I feel like.
Now, because there are many possibilities there, and you do 3D printing. So in the I think 5 years ago we were testing cylindrical membranes, and we didn't know how to deal with them. So now you can do 3D printing with this. So it's very nice. So it's very nice if you could test those structures with separation properties in aqueous streams. It would be nice.
Yeah,
it'd be nice.
Oh, it's opportunity, definitely.
Yeah. Questions? Well, I will. Yeah. Okay. There is one question, Liliana.
Hi, Jason.
Hey, Liliana. How are you?
Thank you so much for your great presentation. As always, I just want to ask you a question. It's a general question, okay? So for me, the work is not new because I'm following you more or less in all the papers. You know that I'm your fan. But my question is a little bit general, okay? So you have seen that you can 3D printing the most of your ionic structures, and it is very, very interesting. But my question is, do you think that property would, let's say, impact in terms of gas separation? For instance, if you could prepare some fibers by 3D printing and assembling a model, I don't know if you have thinking on this, but do you think it could be an advantage directly for gas separation or more for other applications?
Yeah, I think that's a good question, right? And we don't know. I mean, even I think conventional materials with 3D printed membranes, how that would influence the properties, because maybe the alignment is different. Some of these effects are just different if we're 3D printing something. And I mean, the chemistry of the material is still the same, but the polymer backbone may be created differently. So whether it's membranes or other applications, I think, yeah, 3D printing changes your morphology perhaps, and it may make it better, it may make it worse, but it's worth trying.
Okay, thank you. That's my question, because if we can use also morphology, it would be very interesting, no? Because you play a lot with chemistry and it gives you a lot of work. It's difficult to reproduce sometimes in large scales. So if we could use a technique that also impact our performance of our materials, but just by changing a little bit morphology, I think it would be great, no?
Yeah, absolutely. And I think too, even just the surface, if we can make a very thin surface and put ionic liquids onto that surface, maybe that's all that's needed, right? Like I showed earlier, we're soaking the membrane in ionic liquids. Maybe I don't even have to soak it. Maybe I just need to put some ionic liquid on the surface of the membrane, and that changes everything as well, right? That it's, and maybe the surface is creating a barrier because of it's with the air when we're making the films, and if I add ionic liquids just at the surface, it changes that surface enough, and that then increases the gas permeability. So yeah, I agree. We can do all the chemistry we want, but it does take a lot of time. Yeah, and just the processing.
Thank you so much again, Jason.
Sure.
Okay. Thank you very much again, Professor Jason Bara. Thank you very much for coming here and share your research with us. I don't know if you have some words for the community.
Oh yeah, I mean, thank you again. It's my pleasure to be here. And yeah, I would encourage everyone. I think polymers and ionic liquids is still a very understudied area, and there's just lots of opportunities in it. And yeah, it takes a bit more chemistry, as Liliana was pointing out, to make some of these things, but there's many opportunities. And even like you said, there's no studies on really aqueous separations in these kinds of materials. So probably if you can think of it, it's possible with ionic liquids and polymers. So I encourage more people to get into this area.
Okay, thank you very much. And thank you all the audience for coming today to this webinar. And in 2 weeks, we will have another webinar for you. So see you there. And thank you very much, Professor Jason Bara, again. Bye-bye.
Thank you very much. I appreciate it. Bye, guys.